Let's look at the Rigel inexpensive $1,500 spectrum analyzer with tracking generator with regard to its tracking generator performance. I am going to do this at the 0 to 500 megahertz region to start with because this region seems to be where it performs the best. There are some issues at higher frequencies with leakage, and we'll get to that in a later episode here. But anyway, let's take a look. As you can see, we're going from 0 to 1500 megahertz, and it starts rising in the 700, 600 region here, and loses about 5 dB of signal to noise by the time it gets up here. And if I go to tracking generator, put the level at 0 dBm, and then turn on the tracking generator with this switch, you see that the noise level, even at 1 megahertz bandwidth, rises a little bit. All right, we'll turn it back off. But this is not a level we would normally be using for doing tracking generator type work. We have a 1 megahertz receive bandwidth here, and we have a video bandwidth of 1 megahertz, both of which are well more than what we normally would be using. Let's put it at something more reasonable, like maybe 30 kilohertz. We'll hit bandwidth, 30 kilohertz. That drops down into a more reasonable range here. Then let's say the video bandwidth could be put at 10 kilohertz, because most audio that we're going to use is not going to be broader than that. And so it's a reasonable number. We have a 5-second sweep from this end to this end, and we still have this rising characteristic. But unlike before, we have more leakage because we have better sensitivity. Let's look at that. Tracking generator gives you this screen here. Turn it on. Aha! Now we have quite a little bit of leakage going on, especially after here. And that's around 500 megahertz. Let's use a marker and find out for sure. Yep, thereabouts. Here's 500 megahertz right here. So that's up the curve a little bit. Let's use the 500 megahertz as the upper end. So let's set frequency. Start frequency. Let's go 1 megahertz for that. We're not really interested below that in this case. Stop frequency. Let's go to 500 megahertz. Now you see our sweep, due to the automatic features of this unit, goes faster, about 1.8 seconds across the screen, as opposed to 5. We do get this slight rise here at 500, but by and large everything below that is at the same level. So that seems like a more reasonable place to use this thing, but we will do some stuff in another tutorial about what happens at the upper end. So we have that. Let's take a look at, now I'll show you there's no extra leakage due to these cables. So if I have this set for 0 dBm and I put this in, the expectation is that we'll have 0 dBm minus some cable loss here coming out of this thing. Well, there we go. Now we do have a little burble here and a little burble there. Due to the switching points in the DSP generation function, I would presume. But let's just leave that the way it is. That way we don't have to fool with anything. And see what happens when I put a low-pass filter in place of... no, actually, let's put this band-pass filter in first. This is a very narrow one, so I wouldn't expect it to get to the full peak because of the resolution. But anyway, let's look at it, see what it looks like when I put it in the circuit in place of the barrel here. So there we go. Now we see that the ultimate is about 72 dBm, something like that, minus 72. And we have some loss at the top here. It's actually showing a little more loss than is actually there, I think. Let's hit the peak. It says it's 156.521, which is not quite the frequency that's here. This is 156.125, actually 157.125. But remember, we're sweeping a long distance here. And we're seeing some strangeness up here, which could be the filter or could be this unit. But we also see a spike here, which is probably a spike in this, but it's all below 60, which is the reference line I have here, display line. Oh, display line. Hit System, Display, Display line. There it's off, there it's on, and now if I want to, I can change it to something else. I'll leave it at 60. That's a good number. So there you go. Since we haven't done any equalization or anything like that with this unit, let's zero in on this. So we'll go to, let's see, frequency, peak to center frequency. That puts it in the center. And then let's go to span and make it 200 kilohertz. 200 kilohertz. Now for some reason, our frequency, as I said, was not very accurate. So let's put it at 157.125, which is what is marked on this. 157.125. Oops, I'm on span. That's not what I want. Frequency, center frequency, 157.125 megahertz. Ah, right there. Fairly accurate when you're in a spread that is not real wide. And this little burble here is typical of all of these filters. I happen to know this filter is one that we sell at Telewave where I work. It's made by Piezo Technology and Mtron. And it does match what it's supposed to do. We can use the markers here if we wish. We're on marker number 1. We'll select it as normal. And we'll run the marker around here if I can find it. Where's the marker? Well, let's go to the peak. There's the peak. But let's go to the let's go to the center frequency here, and we'll then go to back to the marker and make a delta, and we'll go down 3 dB here. So we're at about 3 dB, 2.9, almost 3. So now we'll make that the normal marker. All right. And as you see, it's 8.9. So we have some loss here in this filter. Then we'll go to marker 2. We'll put that one on the center frequency. So hit normal, marker 2. Well, we'll just put it on 157.1250 megahertz. There it is. It says it's about 6 dB down from the 0 dBm here, which is about what the spec on this filter is. And so that's that. We'll go to number 3 here, turn it on. All right, put it at the 3 dB down point. First, let's leave it on top of this one. Go to delta, go 3 dB down. Okay, then go back to normal. So I got 3 points on this. And then the fourth one we'll use as our low level point. So we'll go down to the 40 dB bandwidth, which is, or the 50 dB bandwidth, which is right about here. So it's 50 dB down. over here at 157.164. Now again, I can do the same thing if I want to find out how far up and down that is by putting this here, going to delta and going up here, and at 40 dB down we're at plus 35.6 kilohertz, and at minus 40 on the other side we're about minus 34.3. So there you go. So let's look at a low-pass filter. I also have one of these from work, a Telewave product. It rolls off at around 168 megahertz. So we need to go back to where we were before on this. Frequency start 1 megahertz. Stop 500 megahertz. So now we're doing that whole span again, and we can now put this low-pass filter in here. Type in connectors on this product. Runs about 100 watts or so, can go through this thing without any serious problems. So there we go. And you can see that we are a very low loss up in here. And then it starts dropping down here. So let's see what our markers say about all of that. So we'll hit marker. We'll hit number 1, normal. And we'll see where that marker is. And we'll go down here at the low frequency end. And down here at 1 megahertz, or let's make it 7 megahertz, which is about 40 meters in the amateur community, and it's about 0.63 dB down there. It's actually probably less because there is some loss in these cables. Let's go to 2. Let's find out where the thing starts dropping off, where the shoulder is. So we'll take number 2 here, and we'll roll along here and see where it drops down to about 1 dB. Looks like it's there, which is 167.33, very close to the 168 that I said it would probably be. We'll go to marker 3 and get the 3 dB point, another common frequency that's used for filters. There we go, and that's at, let's see, 198 megahertz. And then 4 will tell us where this thing has actually been set up to null out, to reject. Looks to me like it's 65 dB down at 161.571. Oh, that's a delta marker. Excuse me. I'm on delta. See? Normal. that didn't make any sense. It's 318.696. Now, I have this scan here. Looks like we start coming back up here, which is not unusual, but it's still less than 40 dB, or more than 40 dB down at 500 megahertz. So it's doing what it's supposed to do, and it's displaying what it's supposed to display. So that's the important point here. Let's try something new here that we haven't shown in this episode, and that is how we can put this into the normalized mode, which will give us a little better accuracy in our readings. Plus it will provide us with a zero reference that excludes the cable losses and so forth on the spectrum analyzer here. As you see, we're down a little bit here. Like a marker 1 is at 1.84 dB down. It's really not down that much, but the combination of ingredients here is making it appear that way. So let's put this back together this way. So we have 0. All we have now is a cable loss and so forth. And you see it's still down all the way across here. That has to do with the levels that are coming out of this signal generator, the losses in the cable, whatever, in this variation due to the tracking generator. Well, what we can do is hit tracking generator to get this screen. There's a normalize here, hit that. Didn't appear to do anything because what you need to do is turn it on here. And I've also set this normalized reference level to 10 dB because that'll drop this from up here down to here so we can get a better view of this line. I've also hit the system button display, and I put the active function here to the center so it's down here out of the way of this trace. So that's the system button where that is, display and system button. So let's go back to tracking generator, and let's now hit the normalize button and turn on normalization. It's updating the reference trace. It'll take one scan to do that. Then it'll take another scan to put it right on the line. So all of those now will be at, well, let's go marker, 0 dB. There's nothing is out of calibration here at this point based on what the thing has done by normalizing the system. You still see we're at about 72, 71 dB here. We'll put our filter back in. Now we see pretty much the same curve. The only difference is now we're seeing things at 0.2 dB, which is actually closer to what the spec for this product is. That's at 150 megahertz, or well, 149.868. Okay. Number 2 is at 0.99, so it's very close to 1 dB down, which is where we wanted to be for the corner. Number 3 is at 3 dB down, 3.01. That's close enough. And number 4 is still in this notch down here at 70.31. Now this thing is reading a fairly accurate representation, in some of the ripple and so forth, and variations due to cabling and so forth have been taken out of the equation. Now let's say I would like to save this trace. Well, saving the trace by itself without being able to step through the different markers here might be useful, but let's do one more thing before we do that, and that's to hit marker again down at the base here. Oops, sorry. We'll hit get the second channel. And we're reading frequency here. Turn the marker table on. Aha! Now we have all 4 of those traces, their frequency, and their amplitude. So we have 0.21, 0.99, 3.01, and minus 70.77. And I can now save this. And what I do to do that is I hit the little print button over here. I get this box. This is a Telewave TLF150. So let's, this is now in numeric mode, so let's hit our button down here. We don't need Chinese, I don't think. It's a Chinese product, of course. We'll put that in capitals by hitting the 1 here. Now we'll go T, enter, W, enter, space, then T, enter, L, enter, and F, enter, Then we'll hit this to go to the numeric mode again. And we'll go 1, 5, 0. You don't have to enter the numeric digits, as it turns out. I'm happy with that name. I can backspace here if I need to erase something, but I'm happy with the name, so we'll just hit OK to save it. Saving the file is completed onto this flash drive that I have plugged into the USB port on the front of the instrument. So that gives you an idea of some of the other features that this particular unit has that are very helpful, I think.